All right, so this is going to be a bit more of a technical talk. I'm going to do my best to put things in relatively familiar terms, but I know that again, may get a bit technical, so please do comment in chat if you need any terms explained or anything as I go through this. But what I'm going to talk about is the work that I did in combination with Andy Watkins in particular earlier this year on getting server-side compute set up for some aspects of Eterna. So as some context for what we were doing and why, so of course with OpenVaccine, we had these novel degradation predictors that had been developed where both from the DOS lab and from, for example, the Kaggle competition we launched, we had these new tools available to us to be able to predict how well our mRNA would actually hold up, which the whole point is stabilizing these to be able to make more effective vaccines. And ideally, we would be able to turn that into design time in silico feedback. So as you're actually working on your design, being able to get immediate feedback on how well we're predicting you might do. Now, what we do typically with just predicting what structure your sequence will fold into is through the energy models is those are all run locally in the browser using technology called WebAssembly. And that has made huge strides, but it's still not magic. It does allow for high performance calculations within the browser, but trying to get these predictors, particularly based off of machine learning systems, to actually compile in that environment and such, turned out to be a bit of a headache. And also on top of that, working with a spike protein, which is huge, and it's just straight up really expensive calculations that take a long time. And so as we went and thought about it, what we decided to do is to look at moving these computations server side. So the naive approach for how to do this would be to just get one very large server and put a web server on it and say, okay, so we'll just be making all of your individual browsers will be making requests to this server, and it will go and do all the computations. We could do that, but there's a lot of downfalls with doing it that way. One of them is that dealing with concurrency winds up becoming harder. So as we're trying to serve a lot of different people at once. Another aspect is basically scaling. So both as when there's not a lot of activity going on, we don't want to be using a lot of expensive resources. We don't want to have a very large server allocated when we don't really need much, or what happens when there's a lot of people playing at once. We need to be able to address that. So the next logical step from there would be using auto scaling and load balancing. The idea here is just starting off with the load balancing is that, or actually I'll go the other way around. So what auto scaling does is say based off of how much resources we're using is we'll be able to dynamically add and remove the number of servers that we have running. So if we we start out with say one server and say, okay, so we're getting a lot of requests, we're out of memory, we're out of CPU, it'll automatically say, hey, we need another to spin up another server to take some of that load. And then what the load balancer does is it intelligently chooses one of these servers that has available capacity and says, okay, I'm going to forward on this request to that specific server. And then the environment of these servers. So whereas with an individual server, you can just kind of log into it and set up the server and or set up the software and get it running. As much as we're trying to migrate away from doing that anyways, you really can't do that with this setting, because you need to, if we're dynamically adding and removing servers, they need to be able to set themselves up as they go. So a couple ways to do that is using machine images to basically just make a clone of the the disk in particular. Another option is using something called code deploy, which will basically automatically run some scripts when new versions of code come out or when we spin up a new server. But there's still another problem with this approach. What if we have a really tasks with a really wide variety of resource requirements? At the time when we were planning this out, it looked like one of the prediction tasks could have used up to like 90 gigs of memory or something like that. It was very, very large. We don't want to have that allocated more than we need to, for sure. So how do we deal with the fact that we have some situations where we need a lot of compute versus somewhere, we need very, very little. And so we need to be able to balance these different types of tasks across these servers, and we really want to be flexible with how much we're allocating based off of the types of tasks that we want to run. And in particular, if some will be inactive for really long periods, especially if they're very large, we really want to be careful about how much we're allocating. So the next option is what's called serverless, which you might think means that there's no server, but that is not quite true. It just means that you don't have to think about the server. And in particular, it uses something called it's typically implemented as something called functions as a service. So the idea is that you just say, okay, so here's you have a block of code that runs, and it has an input and it has some output, and then the environment itself will decide when to spin up servers and whatnot, and handling concurrency and all that. That's all handled, that's built into the tool, basically. And so this is super easy to scale. You just make more requests and it will add or remove servers as needed. For the environment, you can just provide some basic code. We need a little bit more of an extensive environment, so we would use what's called Docker, which basically, it's sort of like a machine image in that you're basically defining what's on disk, the programs that are available and whatnot. But there's still issues here because there's limitations to how much resources you can use with serverless. There is a hard cap on the amount of memory and CPU you can allocate based off of the way that Amazon has set this up. And also, another big issue is timeouts. So these, even with the compute, we can't just allocate more compute to be able to make things faster, because some of these predictors will often, how should I say, it's the individual tasks themselves can't take advantage of additional compute because they're running they're running their tasks in particular in serial instead of in parallel. So we run into an issue where things will just take a long time anyways. And in particular, this step over here, this HTTP API, which is the AWS API gateway, there is a hard cap to how long the timeouts can be, which was shorter than the amount of time that we needed. So this approach still won't quite work. The next option that I looked at is something called ECS and Fargate. So this again takes advantage of Docker containers. And you define tasks and services that you might want to run. So tasks being things that you want to do one-off versus services which are long-running. You specify the resource requirements you use, and then it will actually create instances of these containers to be able to run whatever you're looking for using available capacity. And so with ECS, you give it a bunch of servers to deploy these containers to. So a given container is kind of like a virtualized server. You can kind of look at it like, and so you can run multiple on one server. So with ECS, you can deploy multiple to, you give it the set of servers that you want to run on, and then it will instantiate the containers. With Fargate, it manages instance creation, and it manages the operating system and the stuff required to run Docker. So you don't necessarily have to do as much manual work to make sure that that's all working properly. But there is also a limited amount of resources you can allocate again. So there's a cap on memory in particular, which is what we were running into when we thought we were doing these very large tasks, or that one task in particular that we thought was going to use 90 gigs of memory. Didn't wind up happening, but that was a potential problem that we're going to run into. So what we wound up using was based off of a recommendation from a friend. What I looked into is something called AWS Batch, which is a service which provides you a job. You can set up job queues with priorities for your tasks, and you can define your tasks, including the dependencies, and it will automatically instantiate and allocate the containers. But it's taking, and there's less restrictions on the amount of resources used as well. And it's really defined for doing, really what it's designed for is batch processing, but it's really works well for this task-based model. And showing this video which has some nice visualizations, as you can see that as tasks are coming into this queue, is that it's picked. This is the higher priority queue. This is a lower priority queue, and the different tasks, or the different colors rather, on these tasks represent the they're different types of tasks, and I believe the red one has to run first, then the green, then the blue, and so it will make sure that the red ones are running first, and then it will go and run the other ones. And then inside here, you can see that these are individual. Each of these boxes are individual servers. And you can see there's different sizes of servers that are provided that work for different, that are in particular based off of the amount of resources needed for a given task. It will allocate a different sizes of servers. And you have actually two sets of servers here. The one on the bottom is what's called spot servers, I guess, which is basically a market for extra available compute, which is cheaper, but isn't necessarily always available. So we can set this to send jobs there if there is compute available at the price range that we're looking for, which can as a way to help reduce costs while still having the reserved compute. Trying to remember if there was anything else I want to cover. I think that may have been it. And you can see towards the end, it automatically removed instances when needed. And then we set a cap for the maximum amount we want to be able to allocate. So going now to how I actually wound up implementing this. So I started out, I actually did wind up using load balancing still. But what I did is so coming from the client, you will be hitting what I refer to as an ingress server. So something that is responsible for actually getting these jobs queued, which is available, something that the client can talk to. And that is an auto-scaled set of servers with a load balancer. And I used Flask to implement this API, and also inserted a Redis cache. So instead of having to, every time you make a request for the prediction for a given solution, instead of having to recalculate every time, we're caching the results. So you can see here that we have the request going through the load balancer, hitting one of the servers in the auto-scaling group, which will check in the cache if a result is available. If not, it will start a job on the AWS Batch, which will then write the result to the cache, which the ingress server will be waiting for, which will then wind up returning it to the client. And then on the right here, we have the container image put in the repository, which is what AWS Batch is using to get the code that actually will wind up needing to be run. It's defined as a container. And then the given task in Batch is, I just say, this is a container you should be using to run these jobs. And now to actually get this deployed, I add another layer here using what's called code pipeline, which basically means is that in our GitHub repository for this these services, when I make an update, when I push an update to GitHub, it will automatically notice that the repository changed, and it will do what's necessary to both send out the update to the Ingress servers, so taking and grabbing the dependencies needed for this Python web app, roll out the update to these servers, and then also it will build the Docker container images from the definitions that are contained within the repository, and it will also send that off to be put into the container registry. And then also, so a couple particular technologies we're using as well is the Amazon Cloud Development Kit, which allows us to define the actual, like all the infrastructure. So like the specific servers we want spun up, the batch jobs, the container registry. We can define that using TypeScript, using code. So instead of just clicking through the UI, which is a way to help us make sure that it's easier to kind of, if we want to go back and remember what we did, it's easier to do that. It's very easy if we wanted to duplicate the setup, for example. It's a way of kind of self-documenting. And then another part of this is we're using Ansible for, so whereas the CDK is used for defining the infrastructure that we're deploying on, Ansible is used for actually managing that infrastructure. So Ansible in particular is used for the Ingress server and handling things like some dependencies on the Ingress server and whatnot. It will handle that. And a handful of future work to do is just using this more. Both in game, we've talked about using this or similar infrastructure to be able to even just do regular folding calculations. Other services that we run, for example, Eterna could definitely make use of this kind of setup. And the Wami charts, if anyone remembers that, it could also take advantage of this. Another step is doing partial caching. So right now is that if some of our jobs are actually kind of multi-step, is you have to get a result of a fold or the partition function or something like that, and then you'll go and do a prediction on it. One of the things that we could do is just cache, for example, the folding engine computation, so it could be reused across. If you want to get two different types of predictions and they both use the result of the partition function, then we could just only compute that once. So doing this kind of partial caching is one improvement that we could make. Improved handling of timeouts and failures. Right now we have something that works, but it could be cleaned up a little bit. Latency reduction is a big one. If we wanted to use it for actual folding calculations, right now there is kind of an arbitrary, I'll say 10-second delay between when you request the job and when you actually get a result back, even not including the time to do the computation. And that's due to the way that AWS Batch is structured. It's meant for batch jobs where you don't necessarily need a result real time. And it optimizes basically for cost is a big thing. You don't want to spin up, you say, okay, I have one job. And so it spins up a job for that, and it's still completing. And then, oh, I have another job, and you just keep spinning up a lot of small servers, as opposed to saying, well, let me just wait a little bit to see if I get more jobs, and I'll just spin up one larger server, which is winds up being more cost effective. But there's definitely some tuning that we could do, or maybe even not necessarily using batch, but using maybe a similar service to that. There was one that I was pointed to, or going back to using something like ECS and kind of doing it more, rolling it our own. Or even with Fargate, we might be able to take advantage of some of that now, but it would require a little bit more work. But definitely, if we want to use it for things that are more intended to be real time, then there's definitely some work that would need to be done there. And also, finally, doing some rate limiting and abuse protection right now. That is pretty limited. You can kind of make as many requests as you want, and they'll just get queued up. But there's definitely more we can do to be able to say, hey, wait your turn. You can submit all these jobs, but you might need to, make sure that other people get their turns or whatnot. So there's definitely more that we can do there to improve. And thank you very much. That is a quick run through of the work that I did. And I did not pay as close attention to the chat as I wanted to, but I will go back and look through. Just how do we compute? Yeah, I think that was a response to the to the previous question of what this is about. How we compute efficiently for Eterna with big loads is, it's all about really scaling and being able to have more compute available when we need it. How does this compare to in containers? I believe that was referencing AWS Batch. AWS Batch actually, I'll back up a second. AWS Batch, there we go, actually uses containers. So you give it a container to run. So you say, here's the container image I want you to use to run the code. And for example, we have basically a Python script that calls a C++ executable that we compile. So that's our container image, which includes all of the code and the runtime, whatever we need for it to be run. And what AWS Batch does is it says, okay, if I need to spin up a server, I'll spin up a server, and then I will actually create an instance of that container on an available server that has enough capacity. How big a load has eternacon maxed out to? I don't know for sure. That said, the way that I have it configured is I think a max of 24 cores or something like that. In memory, I don't remember how that scales with memory, but and yeah, Guz, your question about Python. Yeah, what we're using for in this case is it's a very lightweight Flask server to actually take these requests in this ingress step, and then on the individual containers on the individual jobs that are running within batch. Again, it's lines up, the majority of the work is getting done by, well, it's not always C++. Sometimes it's other Python code, like the Kaggle competition. Usually what they give us is some Python code to run. But basically it's just, we have a simple Python wrapper that goes and calls the related code. And Riv, as far as being able to donate CPU resources, that's actually folding at home is the right direction to think about. And what folding at home runs on is something called Boink, which is a distributed computing platform that basically you download the Boink client and point it to say, hey, I want to work on this project, like folding at home. And it will say, hey, if you have spare computer resources available, it will then go and run those jobs. Same thing with Rosetta at home, and there's a number of other projects. So yeah, totally, we could take advantage of something like Boink, although of course, you need to some degree a critical mass of people actually running it to be able to make good use of it. And reliability is an issue. Well, what happens if there aren't enough people available running it? You might be able to say, well, that might be an interesting cost saving measure. If we use people's donated compute, if it's available, maybe. Though there's definitely a lot of there's definitely still work required to actually hook into those kind of systems, and we need to set that up. How long does it take to compute the Eterna fold algorithm for each design? I couldn't tell you offhand. I'll say it, and it obviously depends on the design, but it wouldn't be significantly faster than if you had a good CPU in your laptop. That's essentially what we're doing, is we're just saying, hey, we have some high-end CPUs that we have available. So it might still take a solid few minutes to get results. I don't know, 3 to 6. It's just it takes that long, and having more cores doesn't fix the problem because these problems aren't parallelized. Are each of these loads streamlined, or do they have a lot of fluff which weighs them down when they enter the pipeline? I guess it depends on what you mean by loads, and depends on what you mean by what would weigh them down. I mean, when you're requesting something like, say, I want the I don't know, the DEG score for this design. There's a request made to our ingress server. It checks the cache. If not, it sends a job. Yeah, I guess I'm not necessarily sure what you mean by load. And yes, blockchain has nothing to do with this. That is a distributed consensus model based off of proof of work. But that is unrelated to this discussion. All right. If anyone, I know this is kind of a whirlwind tour of what I've set up, but if anyone has any more questions, feel free to reach out.